All right. So let's talk about confidence intervals now. So at this point, I'm assuming that we have a decent understanding of sampling distributions and all the stuff that was previously covered. So moving on with that. Right. So before we start with anything, I actually want us to look at an example, and that's where we'll make some interesting observations. So Uh, so the American Express Retail Index provides information on budget amounts for home improvements. 45 home improvement jobs in the United States were randomly sampled, and a total expense of $129,849 was recorded. Right. So basically, the question is stating is that we took a sample of 45 homes and their total cost or the total expense for all the home improvements was 129,000. Uh, right. So the question is asking the first part, find a point estimate for the mean budget of all improvement home improvement jobs, right? So point estimate, now this is something we studied, right? We should know what the definition of a point estimate is, and that's pretty much all there is to this question, is knowing this definition. So a point estimate is something that you use, right? So point estimate for the mean budget would be some statistic of the sample that you can use to estimate the mean of the population. So the sample mean, as we talked about, is a good point estimate, or it's something that we can use as a point estimate for the mean budget. So we have a sample, right? And we have the total expense. So what the average expense is just going to be the total expense divided by the sample size. So 1298459 divided by 45, right? So that should give us our sample mean, which is a point estimate for the total mean, true mean. And that's about it. Yep, so we can use the sample mean as a point estimator. Therefore, we get our sample mean, which is the point estimator for the population mean. Right, so uh, the next part wants us to compute the sampling distribution of X bar, right? Sampling distribution the of a sample of size 45. Assume that the budgets for home improvement jobs have a population mean of 3050 and the standard deviation, population standard deviation of 1350, right? So they've given us the population parameters and they're asking us to compute the sampling distribution. Now, uh, again, there's something we should already know, that the mean of a sampling distribution, especially one with a size of 45, uh, is not only going to be normally distributed, but is going to have a mean that is equal to the population mean, uh, which is 3050, right? So that's our mean, and then our population standard distribution. No, sorry, our sampling distribution standard deviation. That is something we know, right? So that is our population standard deviation divided by the root of the number of samples, which is 1350 divided by root of 45, right? So that should give us the standard error, or the sampling standard deviation of the sampling distribution. And there we go. So we define the mean and the standard deviation, known as the standard error of our sampling distribution. Mean is simply the population mean, so it is 3050. Standard error is 1350 over 145, it is 201, right? So next part, based on the empirical rule, now if no one is familiar, again, I would expect that everyone is familiar with the normal distribution and the empirical rule, but if in case you're not, let's just quickly go over that. So the empirical rule just tells us that if we have a standard normal distribution, or any normal distribution for that matter, with a certain mean and a certain standard deviation, uh, the proportion, the portion or the area that is covered within one standard deviation of the mean, one standard deviation of the mean, one standard deviation of the mean, excuse my bad handwriting, is around 68%. I believe 68 or 68.4, something like that. And the empirical rule also states that within two standard deviations, we cover uh, 98 point, oh no, 95.4%. And within three standard deviations, we cover 99.7%. So that's the empirical rule. Just thought I'd go over that real quick. So the based on the empirical rule, roughly 95.44% of all random samples of 45 home improvement jobs have a sample mean budget that falls within which two values, right? And does our estimate fall within that range? So, so which two values? He's asking us that between which two values do we have 95.44% of all our random samples, right? So again, we know that our sampling distribution, because it is a large sample, especially because of that, is a normally distributed, right? And has a mean of 3050, which is the population mean, right? It's normally distributed. So within which two values do we get, like there's two certain values. So what is the range of values for our sample mean, which encompasses 95.4% of this whole distribution? It is normally distributed, and like we just discussed, two standard deviations covers 95.4% of our normal distribution. So that means within two standard deviations of 3050 uh, is what the endpoints or what these two values are going to be, and that is what we're being asked for. So the first thing is we need to know our standard deviation, right? uh, Again, don't make the mistake of using the population standard deviation, right? We're talking about the sampling distribution standard deviation, which is this over under root 45, right? And that is equal to 1350 over root 45, or I think we've already calculated that. Yeah, so it's 201.2461, right? Our standard error. So 201 point, let me just check that again. It's 2461. 2461. Perfect. So two standard deviations. So we're gonna have our upper bound 3050 plus 201.2461 multiplied by 2, right? Because two standard deviations ahead. And our lower bound is going to be 3050 minus 2 multiplied by our standard error, which is 201 point something. We don't have enough space to write here. But that's going to give us our two values on the left and the right. And we can see what those two values are, right? So 3050 plus minus this. So it gives us our lower bound 2647. So our lower bound here is 2647. And our upper bound here is 3452, approximately that much. So within these two values, we're gonna have 95.4% of every sample mean that we can possibly get from a sample of 45. So that's something I want you guys to hold on to, right? And the next thing it adds is our estimate. So our point estimate, which we got 282885, right? Does that fall within that range? 2885. So would we expect it to fall within that range, right? We would, right? Because 95%, so most of our sampling distribution, possible values, uh, most of the possible values that any sample of 45 can take lies between those two values, is what we just found out, right? Between 2647 and 3452. So our estimate falls within that range, yes, and because it is within that range, and we would typically expect it to, right? Because in a way, you could say if there's a 95% chance that any random sample that we take uh, is going to fall within that range because it covers so much of the sampling distribution, right? All right. So that brings us to the concept of confidence intervals, right? So Looking at our previous example, we got a 95.4% range. So we can say that if we take any random sample, any random sample of 45 homes, is gonna have a sample mean that's somewhere on this normal distribution curve, right? But because the distribution here is higher, and because we know that within these two values there's a 95.4% probability that it's going to be between these two values. So we can say that there's a 95.4% probability that any sample mean that we get is going to fall within these two values, right? Or another way of saying that is we are 95.4% sure or 95.4% confident that any sample mean, uh, any sample is going to have a mean within these two values. So this is basically a confidence interval around the mean. Uh, yeah, basically. But before we, I don't want you guys to consider this like this is basically a confidence interval around the mean, but typically confidence intervals are used to get a sense of the true mean, right? So let's get to that real quick. So basically, in reality, we typically do not know our population mean, right? That's what we talked about in the start, that our population mean is difficult to calculate because it requires to get an accurate measure of that. It requires you to know every single data point, and that's kind of difficult to get when you're dealing with like 7 billion people or something, right? So what we end up doing is uh, we end up drawing this confidence interval for a sample, right? So let's go back, right? Let's take our, let me just quickly erase this. If you were to take this sample 2885, right, the one we got, right, and if we draw a 95% confidence interval around it, right, so that means we calculate two standard deviations to the left of this, we're going to get something here, and two standard deviations to the right of this, we're going to get something here, right? So we're going to get another range of values, and what that range of values is going to tell us that we can be 95.4% confident that this value here, right, the true mean, is going to be between that range. And that makes sense. Let me just draw it on a cleaner page just to make it more obvious. So if you had a 3050 mean here, right, uh, and if we had a value within 95%, within the 95% confidence interval range of the mean, right, 2885 for example, and then we draw a 95% confidence interval for that, like the same range for that, but starting from here, right, the same length, this same length, but here, right, that length is always going to include this value, right? Because if we were to draw this here, the same length here, right, then this would maybe touch this point but not cross it, right? And if our point happened to lie outside of this range, then that range does not touch it, right? Then it's outside the range. But as long as our sample means value is within this range, if we draw a 95% confidence interval around this sample mean, uh, it's going to include this 3050, the population mean, right? So if we take any sample mean, right, and if we take the range of values for the 95.4% confidence interval for that sample mean, we can basically be 95.4% sure that the true mean is within that range, right? Because most probably it will be, unless we got extremely unlucky and we got some value over here. And that is what we're talking about here, right? We can also look at this diagram. So if our x bar is here, it's going to include the confidence interval is going to include this mu, and if it's outside, it won't, right? Uh, so so if we construct a 95% confidence interval around the sample mean, uh, Does that tell us anything about the population mean? We would be 95% confidence that confident that the population mean would be within that range, is what we just discussed, and hopefully that makes sense to you. So let's further solidify this with perhaps an example. So, so we got the same example, right? So the American Express retail, same example, same sample, right? Now, uh, we got 3050, right? Now the question is telling us, though we had the sample mean again, uh, the question is telling us construct and interpret a 92% confidence interval for mu. So not confidence interval of mu, but for mu. So we're trying to find mu. So we draw a confidence interval around the sample mean, right? So let's try doing this. So we have a normal distribution curve here. We had our 3050 here. We have our 28850, 5.8. So we want to know within how many standard deviations do we cover 92%, right? So within how many standard deviations do we cover? Yeah. So for this, we can just look at the normal distribution. It's basically a normal distribution problem. So let's look at our normal distribution table real quick. So 92% is what we're looking for, right? So here we have our normal distribution table, and we basically want to know we want to basically have 92% from the mean. So basically, we're going to have some area like this that's going to have 92%, basically symmetrical around the mean. So we don't include this region here, right? So again, let me draw that. So 92% around the mean. So let's say, sorry, let me draw that again. So let's say we had a 2855 here. Here we want this region to cover 92%. 92%. So we just got to remember that the normal distribution is talking about everything to the left, not something like this. And there's a way to, like, deal with that. So basically, we got to remember the normal distribution is symmetrical. So what we can do is, uh, for a 92% interval right here, right? This half should be half of 92% because that's also going to be symmetrical and equal. So this half would be 41%. 41%. And this half would also be 41%, right? So we can go back to our normal. So what we got to know is that at point 0, right, we've already covered 50% of it, right? So we want to know at what value z here do we cover 41% from the middle, right? So at the middle we're 0.5, so we want to know a further 41%. So what the value we're looking for here is 0.5 plus 41%. So that's going to be 91%, right? So for 90, oh, sorry, hold on. So it's not 41%, the half of 90 is 46%. So 46% to the left, 46% to the right, my bad for that. So what we're looking for is 50 plus 46, which is 96%. So what we're looking for is a z value that covers 96% to the left. So let's quickly look through our normal table to find that 96% is what we're looking for, right? So that value ends up being very close to this. So 1.75. 1.75 standard deviations to the left gives us that number. And it's symmetrical, so 1.75 on both sides. So this ends up being 1.75. I'm going to talk about a quicker way to do it, but I want you to see how we can conceptually just calculate our interval z values. right? So 1.75 is what we got. So that range is now going to be, the 92% range is going to be 2885.5 plus minus 1.75 times our standard error. That makes sense? Perfect. All right. And that's how we get it, right? Uh, we got our confidence interval range. And what does this confidence interval range tell us? It tells us that we can be 92% sure that our true mean, our true mean, population mean, is hopefully within this range. And go back to the question, right? So we calculate the z-value, we get the confidence interval, we get the range. We can be 92% confident that the true mean has a value somewhere between the range, right? So let's quickly talk about uh, how we can quickly find this, right? So a trick to finding the z-value, which is basically what we just did, but there's like a shorter version, an easier way to go about it without thinking too much. Uh, the first thing is, let's say we want to find the 92% range, right? So what we're going to do is calculate the what we call the alpha value. Alpha value is basically what's left after 92%. So if you're finding a 92% interval, what is left after 92%, which is 100 minus 92, 8%, right? It's the remainder. So we got 8% as our alpha value. Uh, and now what we're going to do is simply find the z-value that corresponds to half of that. So we're just going to find the z-value for 4%, which is 0.04, right? Similar to what we did with, like, finding for 96%. So we just find for 0.4%. It's going to give you the same thing. Uh, so what we're going to do is, hold on, sorry. What we're going to do is go to our z table and find 0.04. Sorry, wrong table, 0.04. We're going to look for the probability 0.04. We're going to look at the negative table because everything below this is 0.04, ends up being 1.75. Same, right? It's minus because on the left side, but basically we're trying to find the number of standard deviations, so minus and plus both count. Similarly, you could find 1 minus that alpha value, alpha by 2 value, right? So that would give us 0.96, and that is how we did it, right? 0.96, and we get 1.75 positive for that. So it works both ways. It's just a helpful thing to know. All right. So we got that. Now, so far, we've seen that the standard error is given by the population standard deviation divided by the under root of the sample size. Um, right? So now, which is this is something we've been talking about, is that in reality it's difficult to calculate our parameters, right? It's difficult to calculate our sample, our population mean and our population standard deviation, because that requires us again to have the data for the entire population, is and that's something we don't always have. That's why we're using samples, right, to basically get an estimate. So so what we actually do is we often end up using our sample standard deviation uh, as an estimate to calculate the standard error, right? So the estimated formula is basically replacing the population standard deviation by the sample standard deviation, which is s over under root n. Now ask yourself this, right? Is this always going to be a good estimate? Sometimes it might not be. So let's think about this, right? What if we took a random sample of the ages of people, right? Uh, and uh, let's say the the actual standard deviation was something 2 or 3 or whatever, right? And we got two people, and we got the ages of 20 for both, right? So our standard deviation is 0 basically here. So is this a good estimate of our actual variance of ages, right? It's very possible we can get a sample uh, with with the same ages, right? Especially if it's a smaller sample, right? So maybe this estimation, maybe using this sample standard deviation is not such a good idea. What if we took a sample of 20 people, right? Uh, Maybe we got someone, two people, same two people, age 20, or like someone got age 30, 40, 35, and so on. So you can kind of see that the larger the sample we have, uh, the less likely is that we get really unlucky with this kind of value, right? With either there's no deviation, or we might end up saying like 20 and 80 with a huge deviation. So the larger sample makes your estimation of the standard deviation more accurate. Again, central limit theorem, right? So again, the thumb rule is if your sample size is greater than or equal to 30, you can use S, the sample standard deviation, as a decent estimate. Right? So basically, it depends. If our sample distribution is normally distributed, then it is a fair estimate, right? And we know that our sampling distribution will be normally distributed if n is greater than or equal to 30 because of the central limit theorem. And here's a quick snippet of when you use which formula, right? So if you want to calculate the confidence interval, the assumptions are that it's a simple random sample of size n, which is usually the case. And if our sample size is greater than or equal to 30, we can assume it's normally distributed. And that's the only time we can calculate this, what do you call it, the confidence interval, right? So if we know uh, our population standard deviation, we can simply use the population standard deviation for our standard error as the most accurate one. But if we don't know it, we can use our sample standard deviation. Now, if we had a sample, sorry, yeah, so we don't know it, right? So we have to use S. And let's look at the example quickly. So a random sample of 1,000 students gain an average. Right, so a sample of 1,000 students gain an average of x bar 22, right? So the mean 22 on their second attempt at the exam, SAT exam. And the standard deviation S, remember, S is a sample standard deviation, is 50. Now, given 90% confidence interval for the mean score gain, mu of the population, right? So interpret the confidence interval. So first things first, we need to remember that we're dealing with sample distributions, right? So we can't just directly use the standard deviation. We need the standard error. Now, how do we get a 90% confidence interval? We find the number of standard deviations, standard errors of the sampling distribution that covers 90% of it. Now, how do we get the standard deviation uh, of the sampling distribution? So standard error, that is the standard deviation of the population by under root n, but in this case we don't have the population standard deviation. Now the question is, can we use S as an estimate? Can we use S instead of this? And that answer lies in looking at our sample size, which is 1,000, and that's greater than 30. That means that our standard sampling distribution is going to be normal, and it's going to be a good approximation, right? So it's a big sample, right? So it's probably going to have it's going to have a similar or like a close enough standard deviation to our population standard deviation. So we can use it. We can go ahead. There we go. So now our standard error, we can calculate 50 over 100,000. That gives us a standard error. Now, how many standard deviations around our mean covers 90% of the data? So now we're going to do the same thing that we've been doing, right? So we calculate the number of standard deviations, and what we can do this time is simply remember, right? So 90% of the data, what's our alpha? Our alpha is 10%, 100 minus 90. Now we have our alpha 10%. So all we got to do is half that alpha, we get 5%. So what we look for is we either just look for uh, the z value of 0.05, the probability of 0.05, or we just look for the z-value of 0.95. So let's look for 0.05, right? Uh, 0.05, you can look at the negative table. So for 0.05, which is 5%, we're gonna get somewhere in between. So minus 2.5 minus 2 point, no, that's 0.005, I think, my bad. So 0.05, which is 5%. So we get 1 point, get this, right? We have 1.645, right? So it's in between these two values. So we take the average, 1.645. There we go. So that's our number of standard deviations that we need to be away from the mean. Right? And that's how we get it, 1.5, 1.645. We got our alpha value, half that, 0.05. So therefore, we can multiply the standard deviations by our standard error, and we get the range, and we are 90% confident that the population mean is within that range. Perfect. All right. So let's look at another example, right? And let's see if we can try to do it. So volunteers who had developed a cold within the previous 24 hours were given zinc lozenges every 2-3 hours until their cold symptoms were gone. For the 25 participants who took zinc lozenges, the mean overall duration of the symptoms was 4.5 days, and the standard deviation, again, if we're talking about the sample, was 1.6 days. Assume that the population is normally distributed. Got it. So find a 95% confidence interval for the mean duration of symptoms in the population of individuals who took zinc lozenges and interpret that interval, right? So it's just asking us to find the 95% confidence interval again, right? But we just make sure we think about everything, because sometimes there's things that may mean that some of our assumptions may not work. So we know that the first, let's just remember that it's a sampling distribution, right? So remember, when we're dealing with standard deviations, we get the standard error, not, we just don't take the standard deviation as it is, right? So do we know our population standard deviation, right? We don't, right? So we can't get the standard error very easily, but maybe we can use the sample standard deviation, which we do have, as an estimate. Uh, so what do? The problem is that with n is less than 30, sorry, so can we use our sample standard deviation? We can't, because n is less than 30, and that means that it may not be a very good estimate, right? Especially if our original population distribution is extremely skewed. So what do we do in this situation? Now the problem is that with n less than 30, our sampling distribution is no longer normally distributed. So if it's not normally distributed, it's perhaps some other distribution, right? And that's what we're going to look into. Maybe we can work with this, but we gotta use another distribution which more fits what n equals to 25 distribution is going to look like, which is going to be a little deviating from the normal, right? And that brings us to t distributions. So t distributions are basically another type of an distribution which are similar to normal distributions, but they have a thicker tail. So how t distribution works is that it's kind of like a normal distribution, but it's spread out more. There's more variance. It has a thicker tail, right? So it has more proportion of data on the sides as opposed to a normal distribution, where after 3 standard deviations, there's nothing practically left. Uh, so and and remember how we talked about uh, in, what do you call it, our sampling distribution example right here, this one, where uh, the higher the sample size, the more normal it is, right? And the lower the sample size, like let's try with a sample of 2, right? We can kind of see that we have thicker tails, right? So this is in fact a t distribution. it's kind of symmetrical. It's kind of like a normal distribution, but it has thicker tails. Sorry about that. It has thicker tails, and it basically within the same amount of standard within same amount of standard deviations, we might be covering less percentage of the data, right? So that's what a t distribution is, and a t distribution ultimately depends on the number of samples. So the more number of samples you have, the more normal our t distribution is going to look, and the way we go about it is going to be different. uh, Hopefully that makes sense to you. So, and you can see it in this picture here, right? So in t distributions, uh, the distribution depends on the number of samples, and we call that degrees of freedom. So when we're looking at a t table, we calculate our degrees of freedom as n minus 1, meaning 1 less than the number of samples. So for a sample size of 2, we have 1 degree of freedom. So you can see, so for a sample size of 2 with 1 degree of freedom, we can look at the purple distribution, and it has a thicker tail. And as we increase the degrees of freedom, we get closer and closer to our standard normal distribution. So so the more we increase our sample size, the more normal our t distribution is going to become. Uh, so how we go about solving a question where n is less than 30 and we don't know the population standard deviation, we can use our sample standard deviation as an estimate, but we have to use this t table to get our standard deviation, standard deviation values, or the number of standard deviations we're away from the mean. Uh, because so let's quickly try to draw this, right? So if I have a sampling distribution of samples of size 2, right, uh, we get a distribution that is not very normal. It is kind of normal, but it has thicker tails, right? So maybe it's something like this, right? So it has thicker tails. So now the empirical rule is not really going to apply to it. So within one standard deviation, like if you compare it to a normal distribution, right? Normal distribution might be something like this. So for a normal distribution, you can kind of see that within one standard deviation, we're covering a lot more of this distribution, right? We have only this much left on the side, right? Only this much left on the side, but with the t distribution, we have all of this left on the side. So one standard deviation covers less amount of data. Uh, so so now with a sample size of less than 30, we're going to use a t distribution, the appropriate t distribution based on the sample size, and calculate the number of standard deviations we need to be away from the mean to cover the same amount of the 95% confidence interval, whatever confidence interval we're trying to calculate, and get the range of values we're looking for. And you can kind of imagine that for t distribution, the further away the sample size is from 30, the larger the number of standard deviations we'd have to be to cover a certain number of area, right? Perfect. So so we use the t distribution, and we can kind of see here that we use t distribution as t with the degree of freedom, and we do the same thing, alpha by 2, like we take the we get the z score the same way, but we also have to look at the table and make sure we're looking at the right number of samples, or the degrees of freedom. So let's look at the question, right? So so now what we're going to do is we're going to calculate our standard error. We're going to use the t distribution. Standard error is calculated the same exact way, right? Divide by the number of samples under root. We get 0.32. Now we calculate the number of standard deviations we need to be away from our mean to cover 95% of the t distribution, also known as our t-score. So first we calculate our degrees of freedom, which is 25 minus 1, 24. Like I said, degrees of freedom is n minus 1, so 24. And our alpha is 0.1, alpha by 2 is 0.5. So now all we got to do is we got to look through the t table to find the t-score for 24 degrees of freedom and an alpha of 0.05. So let's look at our t table, right? So alpha is 0.05. Remember, we're working with one tail, right? Because otherwise we don't need to do alpha by 2. So for 0.05, we look at 24 degrees of freedom, and we get 1.711, right? No, hold on, sorry, my bad. Uh, so what we're doing is we're looking at two tails here, 0.05, and we're getting 24 2.64. uh, uh, yeah, so because we're not looking at one tail, right? We're looking at two tails. My bad for making that error there, right? Because we said that we don't consider we don't consider this and this, right? If you were only looking to the left, we'd do the one tail thing. So apologies for that error. But we get 2 point, so where was that again? We get 2.64 as the number of our standard deviations that we gotta be away. And back to our question. So we get a t-value of 2.64, and then we can use that to calculate our confidence interval, which ends up being this range. So we can be 95% confident that uh, our true mean is between these two values. And that's about it. That's about it. That should cover all the concepts for confidence intervals and t-values. So you just gotta know uh, when you can use what as an estimate. Just gotta know these conditions, right? When n is less than 30, and then we can use a t-distribution. Remember, for a t-distribution, a population has to be normally distributed. Otherwise, we can't use a t-distribution. So if the population is not normally distributed, we can't use a t-distribution. So just remember the conditions and it should be all good.